All right, we're going to get started here. The couple of quick announcements. The study guide is posted on Blackboard in the lectures folder. The midterm exam will be the midterm exam review will be Thursday in class. Class will be at the normal time, so it'll be at 11:50 instead of 11. So I expect everybody to be there. The exam itself will be on Friday at 11:50, the normal class time, and it'll be open book and open note, right? So you can bring whatever you want. That's everything, right? I don't recommend printing out all of the slides. I recommend you writing summaries of them, because I've had students in the past that have come in and they sit down and they're all confident because they've got a stack of slides about this tall. They're like, I've got the entire class in front of me, right? But in that hour goes by really fast, and all I hear usually from students that do that is shuffling papers the entire time, and most of the time they don't finish. So the goal is to take all of the material that we've been looking at, condense it into a form that makes it easy for you to find information. You can have as many pages of notes as you want, but the act of condensing that into a useful block of condensed notes is actually going to help you study a lot. It'll help you process the information and find the information faster when it comes to due class time. The exam itself is going to be a mixture of multiple choice, short answer, and coding questions. So I will ask you to code by handwritten on handwritten paper, right? I'm going to provide extra scratch paper so that you can do a draft. I highly recommend that you do a draft of your code once on scratch paper and then copy it over to the exam, because that way you're not going back and forth. I know it takes a little bit extra time, but your code will be neater and you won't forget so much stuff, right? So any questions about the exam on Friday? Cool. Check out the study guide. I'm going to ask for Money's points to build the review session tomorrow. So at the end of class tomorrow, please submit, or if you're listening online, email me any topics that you are fuzzy on, and I will include them in the review session. Okay, cool. So I think I got my recording problems figured out. Hopefully it'll work this time. The biggest challenge was finding something that would compress enough to capture a whole hour's worth, and I have a time limit. So basically, I have 50 minutes to get through this without the software crashing. It hits a memory limit at 50 minutes. So, speaking of memory limits, we're going to be working today on expanding, yet again, our Discovering Shakespeare's Favorite Word, right? What we have now, at the end of last class, was a model where we can pass in how many words to keep track of, right? But is that limiting usually? Yeah, by its very nature, it's a limit, right? We're saying track these many words, right? But how many words could there be, possibly?
As many as you can think of.
As many as you can think of. He made up a whole bunch of words too, right? So it's not only just the entire English language, it's things that Shakespeare made up as he goes, right? So what we'd really like to do to be as efficient as possible is have the text itself track the different words, right? So instead of us specifying how many words, the text will drive how many words we're tracking, right? So the idea is that we don't track any words that we don't need to, or we don't reserve space for words that we're not going to need, and that the text actually helps us generate that, right? So to do that, we need a step above dynamic memory, right? We need a dynamic data structure. We need a list that can resize itself. Because right now, we're creating a list that is a fixed size, right? We pass in that size from the command line. We need a list that can resize itself. To do that, we use what's called a linked list. And this is what's called a singly linked list. That means there's one link between every node in the list, right? A linked list always starts with a head pointer, which is the reference to the first node in the list. Every node contains a key, which is the data that we're storing, and a pointer to the next link in the list, right? So the types for heads and the next pointers are all references to other nodes. It's a pointer to the next node in the list. The head is a empty sort of node. It's not a node at all. It's just a pointer to the first node. And then each node, each element, goes to the end until we get to the last node in the list, which has data but a null pointer for the next link.
Does the next and head have an address associated with them?
Yeah, so they're pointers in themselves, right? So it's a variable that holds the location of the first node.
That also has a location.
That also has a location, right? So every variable has a location. So the head itself has a place where it's stored, and it points to the place where the first node is stored, right? But we keep track of the head and sometimes the tail, right, which is the last node in the list, using pointer references.
So each node has locating memory?
Yes? Yes. So we're going to have another layer of structure here that captures whatever data we're storing and an extra pointer to the node, right? So what are some useful functions that we can do with this thing, with these things?
Can add to a
Structure?
Okay, so we want to add to the list. We want to add to the list. What else?
remove,
We want to remove things,
edit,
delete. We want to do what?
edit,
Edit, like how?
like insert a blank that's add.
Yeah. Yeah. We'll stick with add at head, so we're going to add it only at the beginning with this one, right? What else? We got delete, we got add and delete.
Swap or change?
Maybe. We don't really care about ordering in this one. What else? Think about our program, right? What are we going to be storing in each of these nodes?
Data.
The data. What kind of data?
Structure?
But what's in that structure?
Uh,
Yeah, our words, right? So the character strings, and what else?
Indices.
Not necessarily the indices.
Pointers to the next.
Right, but that's not the data. That's the
amount of times they
Frequencies,
occur.
yeah.
right the amount of times they occur. Right. So we're going to take our structure that has a word and a count in it, and we're going to store those as the keys in each of these nodes. Right. So what if we have a list of these? If we have a big long chain of these, what is going to be useful to do with this? What do we do with our array already? What does the program do? So you count, it picks a word out of the file. What does it do first?
Counting the words.
But how does it know which one to count? How does it count the word? We've got the array of all the words we've seen so far, and I got a new word. It's maybe out of the file. How do I know whether or not it's new in the list?
It checks it against everything.
Right, it checks it against everything. So what kind of process is that?
Search.
Right, search, right? So we want to do something like search the list. Right? What else?
Are you talking in terms of what the structure does versus the program?
Yeah. I mean, these are structure responsibilities, right?
Like output wouldn't be a part of the structure.
Nope. So we look for a word, right? That's search. We add it if it's not there. We probably want to delete it at the end to clean up, right? That's fine. There's one more thing that we do. After we've looked at the entire file, what do we do?
Like stop.
Well, we stop looking, and then what? Right?
Then we print it out.
What do we print out?
The actual max word.
How do we find the maximum word?
Besides searching and besides counting.
Well, so this is search for a word, right? And that should give us, searching for a word should give us a pointer to a node that we can manipulate, right? So this one looks for a word, But when we're doing the maximum, what are we doing?
Comparing
Comparing what?
the max score to the current score.
So how do, that's, that, we're not comparing the words, right? We're comparing
All the nodes.
the nodes and the counts in every node, right? So a maximum function for us should find return the node that has the biggest count in the entire list, right? So these are the main functions that we're going to implement for a linked list. Now, to make this, we're going to do a singly linked list, but often you'll see doubly linked lists that look like this, right? And the difference between a singly linked list and a doubly linked list is that there are two directions of links. A doubly linked list, every node not only has the data as its key, but it also, and the original next pointer to the next node in the list, but it has a previous pointer. We can go back, right? And actually we're just going to do a singly linked list, right? But we can do all the same operations, right? So this is going to be a really simple linked list that we're going to implement here.
Are there functions associated with these already built in?
No, there are not. So this is part of the constraints and flexibility of C, is that there are no libraries that implement linked lists, right? We have to build it ourselves. Right? There's no libraries that implement dynamic data structures. So we have to do it entirely on our own.
What about C++?
What's that?
Does C++ have that?
It does. It's called the standard template library. We'll get there. Yeah.
Doing the hard way first.
What's that?
Hard way first.
Yes, the hard way first. And the reason why is because C is as minimal as possible, right? So we can write data structures, the structures that are in the standard template library, the stuff that is built for C++. Those are systems that are built to be generic. That means they include a lot of stuff that we may never use, right? C is built to be efficient. It's built to be specific. It's built to be minimalistic, right? So it gives us all the power we need to do anything on the system, but there's very few libraries to do what would normally be common tasks because we don't want it to be generic. Generic means bigger than it needs to be, right? We want it to be small, fast, and efficient, right? Which means that we have to write a lot of code ourselves.
And does that have an impact on the memory space and everything?
It does, because the simpler, the less complicated it is, the smaller memory the program is going to consume, and the more efficient, the faster the program goes. Yes.
I'm sorry, I kind of walked in late, but
Yes.
before we continue on, can you just quickly explain the purpose of a linked list?
So it's a dynamically growing data structure, right?
Oh.
So we had arrays already that have a fixed size. Even with the dynamic one, we declare at the beginning of the program a fixed size of the array.
Right.
This one, a linked list, allows us to resize whenever we want as we go and only use the memory that we need.
Okay.
Yeah.
So, like the previous, just point to the previous one next, and then like key is like what's inside of stored inside?
Exactly, that's the data that's stored.
Okay.
And we're not going to be doing a doubly linked list. We're going to be doing this singly linked list. We're going to leave out the minimum function. So these are the functions that we're going to run. We're going to be doing a search function. We're going to set up the data structure itself. We're going to do a search function. We're going to do insert functions. And we're going to insert at the head, so only at the front of the list. We're going to be doing delete functions and actually not minimum, but definitely maximum, right? Because those are functions on the data structure, okay? And the search is search for a word. The maximum is find the biggest count, right? So we're going to be pulling some of the functions from our word frequency count library into the data structure itself. Yes?
So you said that we're going to be getting the word that's stored as the data, like the chart in the key, right?
Yes.
But if we are doing a maximum on the count, how is one node going to hold two different types of variables?
We have a structure already, right?
Okay.
So we can just use that as the data in the key.
Okay.
Yeah.
Awesome.
Yeah. so let's start outlining this. All right, so I'm going to push this over here. How am I doing, Cam Studio? I have to make sure this number doesn't exceed 2 gigabytes. Otherwise, I lose the entire recording. So we're 15 minutes in, we should be okay. All right. So we're in my lecture here, and we're going to start off with a header file, right? So we need a header file for our word count. We'll call it, stop that, link list, right? So vim word count link list.h, right? So what do we need?
Still the same word count?
What's that?
Still the same Shakespeare?
Yeah, well, yeah, so it's still the same concept. We're modifying it to use a linked list. And we're going to sort of define a generic linked list and then use it for our specific case.
So the structure first has counter.
Right, so we'll do the same structure. So I'm going to go,
Import everything again,
what's that?
or include everything again?
Well, we're going to use, we're going to redo part of the word funcs part, because the word funcs part is a little bit different. So we're going to do vim word count funcs.h, and we're going to copy this piece and put it in here. All right, and remember, what do header files always have to start with? Right, our declarations, right? We have to do if not defined, define, and our end ifs at the bottom, right? We're going to need, we're not going to be printing anything. We're not going to be doing any file access, so we don't need standard I/O. We will be probably doing string stuff, so we probably want that, right? So we have our structure, right? And this is going to change the entire dynamics of how this thing works. We're going to be using this linked list and the main functions. We'll probably be actually moving these 3 functions over here, right? Because the data structure itself is going to handle finding words, adding words, finding the maximum, right? That's what our search maximum functions are in the add functionality.
And are we just changing out the array to make it a linked list?
Yes, that's exactly right, yeah. And because of that, instead of taking, because these are so tightly coupled to the linked list, we're going to move them into the linked list structure instead. Right? Cool. So what else? What else do we need?
Besides the functions?
What's that?
Besides the actual functions?
Yeah, besides the actual
We
function.
gotta declare the linked list.
Right, we have to declare a node for the linked list. Right? So we'll call this we need a structure called the word, we'll call it a word node. That sounds good, right? And what should be inside of this word node?
The structure itself.
The structure itself. So we need an instance of the word freak. And we'll just call this, what, the data? We could call it the key, we could call it the data, whatever that is. Right? What else does it need?
The next pointer.
Yeah, it needs a next pointer, right? So to do that, what is that syntax going to look like, you think?
No, next.
It's a, well, so what distinguishes a variable that's a pointer?
Asterisk.
Yeah, the asterisk, right? So what type are we going to be pointing to?
Where?
No.
No, it's a what?
A node.
A node, right? What's our node type?
Word freak.
What's that?
Word freak.
It's a
Word
struct.
freak node, word node, right?
Word node.
You can point to something that you're defining, right? So it's not a recursive definition, but it's a sort of internal definition, right? I'm saying that this is a struct word node star next. Right?
Does it matter where you put the star?
What's that?
Does it matter where you put the asterisk? Like, can you put that before or after word node? Like, it won't change anything?
It will. So it won't like it if you put the star here.
Okay.
Yeah.
Does that mean something different if it's at the end?
It's going to try and say you want a struct pointer, but it's not defining what the struct is. So the star goes after, goes between whatever two things. So I could make it the same thing would be saying it like this. So you could do it there, and it's a pointer to a word node, but anywhere else, and it would freak out because it doesn't understand what you mean.
So whatever's before the asterisk is kind of a pointer to that.
Exactly. It's the type of the pointer.
Okay.
Yeah.
Can we put the star back?
Yes.
So wait, what's that line exactly saying then?
This is saying that we want a pointer to something that's like ourselves. Right?
So that's what the next means, like it's
That-
the next node?
It's the next node in the list, right? So I'm my own node. I'm going to point to somebody else, right?
How does it know like which node to point to though? Like, 'cause-
We're going to tell it.
Okay.
Yes. That's what the add does. That's what all of that stuff is. So when we add, we're going to say we keep track of an initial pointer called the head, and that head points to the first node in the list. If it doesn't point to anything, then there's nothing in the list, right? Then when we add a node, we create a new node, set the head to it, and we now have one element in the list, right? Next, we create another new node and put it into the list and make sure that the links are all set. And we just keep doing that as we go, right? So we're going to need some functions, right? We've got a short list. We've got add, delete. We're going to move this. We don't need this in for a while. We've got insert, which we're calling add, search, delete, minimum, maximum, all that good stuff, right? So we need some functions to do this, right? So starting off, let's use the add node function.
The easiest one to start with all the time?
Which one?
Add.
It's a good one to start with because it kind of lays out the entire structure, right? So it's a good way to start thinking about it, right? So what's going to happen? Looking just at the function. Remember it's a header file, so it's just the declarations, right? What are we going to be adding to this list? Right, we're going to be adding a word, right? So we can do, so we'll do add node, and it should be taking a word, so a char star as input. Anything else?
Where the word previously was. To be saved in
Right, so we're adding at the head, so we need a pointer to the head to say I want to add it here, right? So we need a struct word node star head pointer. Anything else?
Why is there asterisk playing out by word? Char word?
Because it's a character array,
Okay.
right? Remember, it's a string, it's a word, so it's an array. Yeah, it's a pointer to the array. Anything else? Whatever the head is pointing to is going to have the next node. So we don't need to we can get that automatically.
So we need to store the word, right?
Well, we will store the word. That's what add node does. It's going to create the word and it's going to store it and put it in the list. Yes.
So the two things that are in it so far, the char, it's the star word, so that's like.
That's the word that we're going to put in a word freak,
Okay.
right? So we're going to create, what add node is going to do is it's going to create one of these,
Okay.
create one of these. When it creates one of these, it's going to create one of these. That's what this does, right? and we're going to copy this word into data, into the word part of data, initialize count to 1, because we've seen it once, and then we're going to link it up using the next pointer and the head pointer into the total list. Right? So that's an awesome outline for what add is going to do. And we'll do it here in a second. Right? Actually, we'll do this all one at a time, maybe. All right, so we're going to add a node function. What should it return?
The value that's the one?
Of what? Value of what? I don't think it should return anything, right? Because it's changing the head, it's changing the list, it's adding to it. We don't have to do anything to the list, right? Cool. I'm going to go back to my other putty window, and we're going to start the CPP file at the same time. Or C file. Is this the right?
Do you normally add nodes to the head?
Uh-oh, am I in the wrong folder?
Go.
Come on.
You can add nodes anywhere. There we go. Okay, yeah, you can add nodes anywhere. Adding it to the head in a singly linked list is the easiest, because otherwise we would have to keep track of where we want to add it. We'd have to keep track of the tail and add it there.
So that's easier than adding it to the end of the linked list?
Yes, in this case. It's a little confusing because we're adding things at the beginning rather than the end, right? Because normally we think of putting things in at the end, but in our case, the order doesn't matter. We're not sorting them. We're not doing anything like that. So, right? Okay. So we need to include count. Word count linked list.h, so the name of our header file, and we've already got our structs defined and all kinds of good stuff like that, and we've got a add node function that we add to the list, and we can start building it. Right? So what was we just talked about the outline for this, right? What should it do first? Right, so that's what it's going to do.
Does it have to create one first?
It has to create a node first. So we'll create a node first. Then what? What's that?
Add the word to the node.
Add the word to the node. What else?
Go to the next, create the next node.
Right, so we want to pile in, we want to link it to the list, right? Awesome. And that should be everything that we need to do, right there. So first off, how do we create a new node?
Create a new structure.
We want to, of what structure?
Word node.
Word node, right? So we want to create a new word node structure, right? How do we do that?
Just give it the same name plus object name and that.
Okay, well, so you want to say struct word node,
Like,
we'll call it a new node,
yeah.
something like that. Is that how we create it? Is it going to exist? Is that going? If we declare it that way, will that memory still exist when we exit the function? No, it goes away. Right. This is a static declaration. Right, which means that it doesn't persist beyond this function. Right. So how can we make it so that it does persist?
Make it a global variable?
Not a global.
In the header? You can't do that?
Well, we could do it that way, but we want to create a whole bunch of these, right? So every time we run this function, we want to create a new one, right? Not just one. What can we use to do that? Yeah, we want to use malloc. We want to use dynamic memory allocation, right? So we're going to turn this into a pointer. So new node is a pointer to our new node. And then we can create it by doing new node is equal to malloc.
But then this is
Yeah, word node.
Word node? Yeah, struct word node.
and that won't give it a specific size.
What do you mean?
What size is that?
What it does is this asks the compiler to count up all the bytes that are in one word node structure, right? So it'll look at the word node structure and it'll say, how many bytes are in this? I've got a pointer, right? How many bytes in a pointer? Do we know?
What is a pointer?
So the pointer is an address, and this is a 64-bit system, so that means all addresses are 64 bits, right? So how many bytes are in 64 bits? 8, right? So that's 8 bytes right there, right? Then I've got a word freak data structure, right? How many bytes are in this?
Same thing, right?
So it's this one here, yeah. So we've got 50 to start off with. Every character is 1 byte, so we've got 50 bytes there. And then how many bytes in an int?
32, so 4.
Right, so there's 54 here, totally. So there's 54 here in that one, plus the 8 from this one, which gives us 62. Right, so a word node, all by itself, is 62 bytes. And that's what we're saying here, is allocate 62 bytes of memory.
For now, and then if we update it, it will update it.
Well, we'll do another one later, right?
Okay.
Yeah.
Can again repeat how you account 62?
So it's a pointer, any pointer that we use, because this is a 64-bit system, that's 8 bytes, right? Plus 50 bytes. Every character is 1 byte, and every integer is 4 bytes, so that's 54 plus 8 is 62. Yes?
And just to be clear, the struct word node star new node, that's just taking whatever's in word node and putting it into, like just copying it pretty much?
No. So this creates a new pointer to a word node. Right? So the memory doesn't exist until we call malloc. That creates a new word node, and it's empty.
Okay.
Right?
So the first, like, sorry, one more time. Can you say what the struct word node star does?
Struct word node star creates a pointer called new node.
Okay.
So it's it's a reference. It says there's an address. This is going to be the address of a word node. Right? Then malloc allocates that memory and gives us the address of that memory, of what will become a word node. Right? There's one thing we're missing. What does malloc return?
Oh, we have to free it?
Not yet.
Oh,
We'll do that later. Do I remember?
Copy word.
Malloc returns a void star, a void pointer. Right? So we have to cast the malloc as a word node star. Right?
Remember I said the new node is going to have the count and the word. Doesn't this only have the word?
This doesn't have anything at this point.
Okay.
Right?
It just has
It does have the space to store it because
Okay.
data, word freak data, includes both the word and the count.
Okay.
Right?
So you have to account for that. That's what
Yeah, our
You have
program
to
is
account
going
for
to deal
what
with
you
that.
want, how much you want your node to actually have.
Yeah, exactly. Yep. Okay, so we've created the node. Now we need to copy the word to the node and initialize the counter. Right? How do we do that?
Is it a loop?
It's not a loop.
Or just like word for the data or
So it's new node.
Assign, yes.
Yeah, but, so this is we're entering some new syntax because we're accessing the members of a pointer now. Before, we just had elements of an array and we would get the members, right? Now we have to access the members of a pointer. So because new node is a pointer, we need to do something like, let's initialize the counter, right? New node data does that. So this says, give me element data of the pointer new node. Right now, this is real. This is static because it's not a pointer here. So to get the count of data, we use the normal dot operator. Like that, right? So data was declared as static. It's not a pointer, so we can use the dot operator. New node was declared as a pointer, so we have to use the arrow operator. Right? And it's just a dash and a gradient inside. Yes?
Does that line of code, the struct word for each data right under the word node structure, does that like let us do data.count?
That's exactly what it does.
So you're just basically copying that word frequency structure and putting it into this
Yeah.
new one?
Yeah. I'm saying that every word node that I create is going to have a word frequency data structure inside of it.
It's
Okay.
gonna be equal to 1.
And we're setting it equal to 1 there.
Mm-hmm.
Yeah.
Could you have said the same thing, just said word freq.count?
No.
No.
Because that would be somewhere else. Word freak.count doesn't exist. This is a variable called data of type word freak.
Yeah.
Yeah.
So what about if we have the word like 2 times or 3 times?
Well, hopefully that doesn't happen. Because we're only adding it if it isn't already in the list. So they should all be the same.
So let's say you have the word there.
Mm-hmm.
So when it comes to first time, it has.
It adds it to the list. And then we only add a word to the list if it's not already in the list.
Also, we go to main.
Yeah. Yeah. Yeah, we'll do that later. Okay, so we still need to copy the word, right? So to do that, what function can we use? String copy. Are we allowed to use string copy?
We have
Will it
to
work for us?
include the string dot.
Yeah, we included string.h already. It's in the header, and the header links that, the include the .h links that up already. So which way does it go? What's the first argument?
What is being copied to?
So the destination, right? So it's the destination first, which will be new node data.word, and we're copying word from our parameter. Awesome. Now we need to link the new node into the list. Right? We need to make sure that it's integrated in there. Right? So we start off with the head. The head is pointing, should be pointing to something. Right? But if it's not, what will it be? If we have nothing in the list, what's that?
No.
It'll be null, right? So
If
how is that different? We've got two cases, if the head doesn't exist and the head does exist.
So if not, no. Or if no, then
Head equals null. What?
Add it to the list.
yeah.
Add to the list, but how do we add it to the list?
All
Well, we can't do that again, because what are we adding? We just created all of it. We're not going to call ourselves. It's not recursive.
Word no.
So what does the head do?
It's a pointer to the next.
It's a pointer to the first element in the list, right? So if the head is null, if it doesn't point to anything, we don't have anything in the list. If we're adding a node, this is going to be the first thing in the list. So what should head point to? New node. It should point to whatever we're creating now, right? Boom. If it's not null, what should it do?
Move.
Do what?
Move to the list until it does.
Well, we're going to add it at the beginning,
Oh.
right? So say we want to look at this. as, oops,
New node equals to the previous node.
yeah, sort of, right?
New node equals to the head.
Right, so if we've got a, oh, we need to do something else, something I almost forgot. Right, so we've got our head pointer that if it is pointing to a node, we need to make sure that the head, the second part is that the head will point to the new node, and the new node next will point to whatever the previous node was. Right?
So heads always point on how you know they're created.
Yes, head should always point to the new node we're creating.
So that's how we're adding it to the beginning of the list.
Exactly, right? So, but before that, how do we make sure the new node points to any existing node? If we are pointing to an existing, what's that?
Can you make it
So how do we do it?
like
New node. What element of new node points to something? No. Word node is a new node, but it has an element called next, right? So we want to make sure that next points to our node. What else points to our node at this point?
Head, something.
The head, right? And it's not .next. Head is just a pointer to the node, right? So we can say new node next is equal to the head, right? And that head is now equal to the new node.
So if head is not null, then it's gonna equal new null? How's that work?
Yeah. Well, it's gonna, so if head is not null, it's already pointing to something, right? And what we want to do is put our new thing in between head and that something. So what we did was, head started out get my head started out pointing to node here. We said make new nodes next
Points to it.
equal to the head, which points to the next node. And then we said make head equal to us, right? Which makes it point in the list, just like that.
So all that's doing is like the node we created, it's adding a
Yeah.
into the link.
It's adding it, it's making the link, it's opening the first link, putting us in, and making sure we link up on both ends.
What if we didn't want it to, because like right now new node is in front of node, right?
Yes.
So what if we wanted to like say after node? So it's
Then we would have to run all the way to the end of the list and get it. Or we could say add after new node or something like that, but that gets complicated if we don't have anything there. So this is the simplest way to do it without keeping track of any more extra stuff. Yeah. Doubly linked lists make it easier because we can go to the end, or we can keep a tail pointer and always keep track of the end. We can add at the end or add at the beginning, all kinds of stuff. Yes, sir?
What is that syntax in the end? The new node next. Like, what's
So this says get the element of the pointer new node called next. Right? So we're
the
getting
element, so like the variable type or
this thing here. Right? So this is another pointer to a word node. And we're setting that next pointer equal to the head. Okay. Now we have to do something before we do any of this to keep, when we create our node, to keep things nice and clean, right? What should the last element of the node, of the list, have as its next pointer? No, right? Do we set that anywhere? We do, right? So when we create the node, we should always set all of the pointers to null, right? That's safekeeping. So new node next equals null. Right, so that makes sure that the last one, if this is the first one we add to the list, then its next pointer will be null, and we know we can keep track of when to stop, right? If we're inserting it into the list, it gets overwritten with the head, so it's okay. Right?
Where do we set up head?
What's that?
Where do we set up head or head?
We'll set up head when we create the list in the first place. Yeah. So the head will just be a handle to the next pointer. Well, it'll be a word node star that we keep track of on the outside as part of our main program. Yeah.
So I don't understand why you say new next is equal to null.
New node next is equal to null.
Yeah.
It's so that when we create our node, we make sure that it's not pointing to anything. Because we could have when we do a malloc, the memory that it gives us might be dirty. It is dirty. It has all kinds of stuff in it, right? So we want to make sure that we initialize it, just like whenever we create a variable, we want to make sure that we initialize it to a known value. And that's exactly what we're doing here. Good? Cool. I believe that's an add. Right? Let's do next what's our next function? What do we write down?
We can search.
You want to do a search?
Oh, no, delete was next.
You want to do delete? Cool.
So the way we're doing it, we can only add and delete the head. right?
At the head, because we only keep track of the head.
Okay.
That's our one place of access. So we remove things from there and we put things in there.
So the newest thing always goes to the head, oldest goes to.
Yep.
And when we're deleting here, are we deleting it because it has a word that we want, or are we making this general, so just delete in general?
Just delete in general, right? So this is, if we have a pointer, we're going to delete whatever this is. We're going to delete it at the head. This is actually what we're going to use for cleanup, right? So we've malloc. Notice we did a malloc here, but there's no free, right? And this is a case where we want that to be true because we're going to use, when we allocate this memory, it's part of a big chain, and we don't want to delete the memory until the program is totally done, right? And that's what this delete function is going to do. We're going to delete one node at a time, and then we'll write maybe a bigger function that deletes the whole list. Yeah. Okay? Cool. So, delete. What does it need? Yeah, it needs a node, so we're going to delete at the head. So we're going to delete whatever's at the front. Right? Does it need anything else? Shouldn't. We're not specific about it. It's just generic, right? So we don't care what node is there. Is it going to return anything? Nope. So it's another void.
Are we assuming that when we delete that node, it's going to take the pointer of that head and point to the next node?
That's exactly what we have to do.
Okay.
Yes. We're not assuming anything because the computer won't do it without us. Right? So awesome. That's exactly what our node function should look like. So we'll put it there. So let's outline this one. Right? What is it? What should it do first?
Point to the node.
Yeah.
What's that?
Point to the node that you want to delete.
Well, the head is pointing to the node that we want to delete. Right? So here we've got either one of these cases. I've got a node and another node, or I've got a node all by itself at the head. Right? The head, we're deleting the node that the head points to. Right?
So
So-
can we just move the head to the next node?
Sure, absolutely. But we want to make sure. Uh-oh, I gotta stop recording. Yeah.